chi-squared test of independence is used if you have many different groups and subject to some conditions, and if you want to know if the two variables somehow have some relationship, if these two are dependent. Just taking a cursory view, you do see that this new drug named Somaquick is going to put people to sleep much faster than the placebo, right? But how would you actually show that using statistics? Last time we did the chi-square goodness of fit test. So if you recall what the chi-square goodness of fit test was, if you had if you just had one variable or one group, one variable, and then you had different proportions, then different numbers here. So it's like if you had like 5, 7, and then 10, so that the total is 22. And then if there was some proposed probability, so let's say these should all be the same probability of 1/3, then you can calculate 22 times 1/3 to find the expected value against the actual value, and you do actual minus expected squared divided by expected squared, right? Expected, right? And then you add them up, and that gave us the test statistic. So we had chi-squared equals the summation of observed minus expected squared over expected, and let's put subscript I here. And then in this case there are 3 values, but you've used this information to get the expected, so really the degrees of freedom is just 2. So you look at the chi-squared distribution with degrees of freedom 2 and see if this number is bigger than something or less than something. That was how we were doing chi-squared test of goodness of fit. And I also explained why this makes sense if you compare it with the traditional test of proportion, especially for the case of just 2 things. It's especially in the case of just 2 it was identical to the chi-squared, identical to the z statistics test for where you use z equals to p hat minus p over square root of pq over n. So this was what we were using to test the proportion, right? And I show that using this or doing the other for the case of just 2 things you can define what a p is, they give you the same conclusion. So kind of explain that. So this chi-square test of independence follows a similar trajectory. You have to compute what the expected value of each cell is, and then you calculate the same thing, observed minus expected squared divided by expected, and then you do it for everything, and then you get the chi-square test statistic. You also have to figure out the degrees of freedom, and then at the end of the day you look at the table of chi-squared and then determine whether the value you get is a normal or not. Okay? All right. So that gives us this first question, which is what is the expected value? Well, in the chi-square test of goodness of fit, you're given a priori proportion for each. But here, none of that is given, so you have to make them up. And the way you make it up is, suppose, let's say, you were given this table. By the way, this table has a name. It's called a contingency table. So suppose you were given the contingency table, and then somehow portion you spilled coffee on us or something, and you completely lost the numbers. And then you're being audited, so you have to act quick. You have to make up some numbers before the auditor will find out. Okay? Now, well, what numbers would you put here? Well, in the absence of any knowledge, you would say, well, you know, this is 150, so I would say this portion is like 17 out of 150. Right? Well, whatever that is. Can somebody give this to me? 11%? 11%. 11 point what?
11.3.
3%. So I know that 11.3% should be residing in these two places, right? Also, we also know that 70 out of 150, which is like what?
46.7%.
46.7%. Okay, good. So since we know that 11.3% should be the sum of these two cells, and out of those two, 46.7% should be this guy, I know that this number should be 11.3% of, sorry, I should really say. So first of all, 11.3% of the total 150 will be this column, right? But then you want 46.7% of 11.3% of 150 to be exactly this cell. Does that make sense? Right? You're just going by the proportion suggested by the totals. That's all I'm doing. Now, if you want formula, since you guys like formulas, you just have to do this. You just have to do 150 times 17 out of 150. That's 11.3%, right? And then times 70 over 150. That's taking 46.7%. So this is 11.3% of 150, that's what it is. And this is 46.7% of 11.3% of 150. That's what it is. Okay, so you calculate this, and what do you get? You get 8, what? No?
It's like 7.92.
Really? What do you get again?
7.93.
7.93?
Yes.
Oh, okay. Okay, good. All right. Yeah, okay. Now, I said you're trying to fake the numbers. Of course, if you're trying to fake the numbers, you should put integers. So here's how it slightly differs from my initial description. You actually want the decimals to be the expected value, to be more exact. Okay, even though, like this would be number of patients, right? Some patients taking placebo happily fell asleep in 30 minutes, within 30 minutes, and they were thinking, oh, this placebo must be the real drug, real thing, right? So these are actual people, so you can't have
0.3.
yes, 0.93 people, but for the sake of computation, these should really be decimals, okay? So what's usually done is you would write down the numbers, 7.93, in a parenthesis, just to be able to compute what should be there, okay? All right, so I'll give you some time to think about what to put right here. Step one of the four-step procedure for hypothesis testing is that you have to set up your hypothesis, you have to write them down. One thing I want to say here is that when it comes to chi-square test of goodness of fit or test of independence, there is no equal sign. You remember how in the, for example, you had hypothesis testing of mean, then usually the hypothesis testing will have the form of mu equals to something and mu bigger or not equal to something. That will be your alternative. So this will be the form of the hypothesis when it comes to testing the hypothesis of a single mean. If you have two means, you still have an equal sign, right? This will be a hypothesis testing of two means. But when it comes to chi-square test of independence, there is no way to write this down as an equation, so you have to be careful. All right, so this is about no relationship and some relationship. That's all there is, okay? Or you can phrase it like this. You can say the null hypothesis is that the two variables are independent, okay? And the alternative hypothesis is that there is some dependency between the variables. That's another way to state these hypotheses. Now step two, what's step two? Rejection rate, right? Actually, this is chi-squared. Chi-squared for degrees of freedom 2 will look more like this. Now I'm saying that the degrees of freedom is 2 is because, see, we're using these information, right? We're using this information, these information. So you see, for each of the rows, anytime you know this value, only 2 are freely variable. This one will be determined once you know these 2. See, to fill in these expected numbers, you have to know these numbers, right? So if you assume that you already know these numbers, and you ask the question like, if this is 5 and this is 26, what's this? And you would say, you're forced to say it should be 39, right? Also, because you know the sum over here, if you know these two numbers, then these will also be determined. So you can see that the degrees of freedom, if you try to vary, you can only vary 2 cells as freely as you want, and the other ones will be determined. Which means that when you do the calculation and try to think about how large a chi-square statistics could be or how low it could be, you're really working with a chi-squared distribution with 2 degrees of freedom. Okay? Now in general, the formula for the degrees of freedom in a chi-squared is row number minus 1 times the column number minus 1. Because you know the sum of it, if your row has, if your column is 3, you have 1, 2, 3 columns. If you know 2 of them, the third one is determined, so it's column number minus 1. That's what's computed here. This will be 3 minus 1. And there are 2 rows, right? Don't include the totals when you talk about this formula, okay? So you have 2 rows, and 2 rows, 2 minus 1 gives you 1. So the degrees of freedom will be 1 times 2, which is 2. And that gives me the chi-square distribution for degrees of freedom 2, and we need to find the rejection region for 0.05. Okay. Does anyone have does TI-84 have inverse CDF? No, inverse chi-squared? Inverse chi? And Spire might have.
Would x squared PDF, would that work or
No, no. You need inverse x squared.
No,
It
it's not
doesn't,
there.
right? Okay. So you will need to use a table. I forgot to print out the table again. Can somebody look up the table for the chi-squared? Tell me what the critical number is.
That's how far.
I can also look it up. Does it have an inverse chi-squared? Yeah, inverse x squared. Yeah, you have it?
Yeah, it has it.
Oh, okay. Then you put degrees of freedom 2 and put
Yeah, that's
yeah, 0.95.
I got that shit.
Is it this one right? The x squared CDF?
it might be.
What did
Yours
you
says
get?
chi,
Like 0.103,
inverse chi, right?
I think.
What
No,
does yours say?
mine just says.
No, no,
X
that's
squared
that's 0.05.
Oh, I have the
You
same
want the
one.
other
Yeah.
end.
Oh, okay.
0.95%.
Yeah, I got x squared PDF and CDF.
Oh, and the calculator just says x squared CDF.
And
Oh.
2.09 sound right or no?
Okay, 2.09 is what James got. So please try this one. Chi-squared CDF of 2.09 and put some high number, 1,000.
Oh, wait,
And
no,
degrees of freedom.
I think this is, I think I'm wrong.
That comes out to like 0.352.
No, that's not it. Then.
Should it be like 7.815?
Try that, 7.85.
where do you get the 7.85 from?
The chart that I found on Google.
Oh. Fair enough.
0.019.
When I put in 7.815, it comes out to 0.02.
No way, that's... Did you use PDF? Should be CDF 7.85 to 1,000.
Yeah, I did CDF.
Degrees of freedom. Oh,
I got this.
oh.
Yeah, that's what I got.
Oh, okay.
Yeah, so in the table I'm seeing it has chi-squared 0.050 with 2 degrees of freedom as 4.605. Okay?
So use that.
Oh, I was looking at the wrong one.
Huh? Yeah, this is the degrees of freedom, yeah. So we use this, okay? So now please check. Put 4.605 CDF, 1,000, degrees of freedom 2. What do you get? You should get something like 0.05.
It's 0.1.
0.1000008.
What?
Point-
Sorry.
It's 0.1.
Sorry. I was looking at the wrong. It's 5.99. Sorry, yeah. All right. So this should give you 0.05, right?
With 5.991.
Yeah, 5.9.
Oh, yeah.
Yeah, it comes up to 0.05.
0.05001.
Right, good, yeah. You get it?
Or just inverse chi CDF.
So the thing is, the usual TI-84 doesn't have the inverse chi-squared. I should be providing you with a chi-squared table. I forgot to print them out, okay?
My calculator has it.
Yeah, the
Yeah,
284
I think Inspire, and what's yours?
Inspired CX2.
Yeah, those have it, yeah. You can put in inverse chi-squared with degrees of freedom 2 and 0.95 in it, and you'll get this number, 5.9. Did you get it?
Yeah, I did.
Okay, great. Yeah, well, you guys will be using a table.
So that's the 5.99, that's one that comes from the table?
Yeah, that comes from the table. Okay, so if you look at the table of chi-square values with, we're going to assume that significance level alpha is 0.05. And if you look at chi-square 0.05, and with degrees of freedom 2, this is the value that you get, okay? So that's going to be the rejection region. If chi-square is bigger than that, that's our rejection region. All right. Now we have to go to step 3. What is step 3? You have to pick the test statistic, right? You have to compute the test statistic. You have to calculate the chi-squared. So what should we do? How do you get the test statistic? It's the same thing as we have done for the chi-squared test of goodness of
It's
fit.
the sum of the.
Yeah, you do 5 minus 7.93 squared, okay? Divided by 7.93. Plus 26 minus 33.1 squared divided by 33.1. Plus 39 minus 28.9 squared over 28.9 plus what is it? 12 minus 9.06 squared divided by 9.06, and then plus 45 minus 37.87 squared over 37.87 plus 23 minus 33.07 squared divided by 33.07. You do this computation, okay? And I have a value here. What was it? I had it. It's 11 point something. I forgot. So, all right. But anyways, if you do this computation and you get 11,
So
what do we know?
it's in the rejection region?
It's in the rejection region. So what's our conclusion? Step 4 is the conclusion. Right? Step 4. We what? Reject or fail to reject?
Reject.
We reject H0 and accept H1, which means that the difference in there is a relation that there is a relation, is some relationship between type of drug and time to fall asleep.